Okay, welcome to the Intelligence Healthcare in its Applications course. And today we will continue our journey and talk about the random forest decision model and its applications. Okay, so before we go into our main slides, then I want to give a brief review of the machine learning methods. So remember in these slides, typically the machine learning will divide into several important categories. And the one is the supervised learning. And in this case, we need to know the label of the data, and we will train the model to learn the data based on the known patterns. So the one key point in the supervised learning is that we must know the patterns in the data. And this pattern can help us to build a model to do the classifications. For example, we may build a model to do a differential diagnosis of the certain disease just based on laboratory data, and or we can build a model to predict a certain state based on the current state or current values of the data. So for example, the weather forecasting or the forecasting the life expectancy based on some demographic data. So that is the one of the application of the supervised learning. And the key point in this one is that we must know some outcome or the ground truth about the data. And in some cases that we don't know the ground truth of the data, we want to use some methods, for example, the clustering analysis, to find out the subsets of the data based on some features. So here we have some pitfall. For example, if we don't know the underlying ground truth of the data, then sometimes we will choose the wrong features. Then the data will be clustered into some meaningless group. So that is one limitation of the supervised learning. But somehow it still has its use. So we will introduce this later using Alzheimer's disease as an example. Okay, so probably we don't have time to introduce reinforcement learning in medicine because it is a very tricky part for you, because in the game AI, we can let algorithm learn from error, but it seems impossible that we can build an algorithm to learn from a medical error. So that is still a very challenging area in the medical applications. Okay, so today we will talk about the decision tree. And the decision tree, actually, it can do two things. It can do classifications, and it can also do regression. So usually we will call the classification and regression tree. And it can be abbreviated as CART, CART. So if you look for the CART and regression tree on the internet, then you will find out many interesting examples. Okay, so one of the capability of the decision tree is to the classification. So for example, can we build a decision tree to make a job offer flow chart? So that is the one example here. So there's a rule node that the first condition is that is the salary at least $50,000. If there's a no, then we just want to decline this offer. Then if yes, then we will also further ask that is this job has the commute route less than 1 hour? And if yes, more than 1 hour. So if more than 1 hour, so we will also decline the offer But if the commute route is less than 1 hour, then we will further consider if the office has offered a free coffee. Then if yes, then we accept the offer. Then if no, then we just decline the offer. So in this model, we have two classifications, two outcomes in the classifications. Either accept the offer or decline the offer. Okay, so accept and decline is the two outcomes of the classification model. Then we will use a series of the decisions to reach these classifications. So this classification can be done at a certain point of the decisions, but we need to go through each decision nodes to make our decisions and to find out our outcome. So that is the very intuitive example of the classification tree. And decision tree is quite common in medicine. For example, here that we can use a simple decision tree to determine that whether or not the patient should transfer to the coronary care unit. For example, if a patient, if we found there is a ST segment changes in the electrocardiogram examinations, then if the answer is yes, then of course we need to transfer the patient to coronary care unit to treat the coronary artery disease. And if the answer is no, then we will still further to find out if there is associated conditions that can predict the severe coronary artery disease. For example, if the patient, we need to determine if the patient has a complaint of the chest pain. If the answer is no, then probably the patient can stay in a regular nursing bed. And if the answer is yes, then we still need to find out if there is some other findings related to the coronary artery disease, then we will determine that we need to transfer or not. So that is a very common example in medicine, and we can use the decision tree to decide the workflow of the clinical practice. Okay, but back to the theory. And so this is a simple example to show you how to do the decision tree. And let me first use the classification tree as an example. So here we have two types of the data. And these data has two features. One is the X and the other is Y. So any triangle or any circle, they can be described by the X coordinate and also the Y coordinate. And visually, you can see that there are two categories. One is the red triangle and the other is the green circle. And you can also see that the green circle is located in the lower right corner of the chart, and the other part of chart is occupied by the red triangles. So in this data, you might be wondering that, okay, so we can use the linear regression, just plot a simple line here, then we can divide the data into red triangle and a green circle. But you probably also find out that if we just plot a straight line here, it doesn't work perfectly because it will still misinterpret some red circle and red triangle as the circle and some green circle in the left part of the line. So regression is useful, but probably not working well in this case. And in this case, you probably want to draw a curved line here, then set to separate the two groups. So that is the one case of the nonlinear regression or classification, because in the typical case I show you in the previous lectures that those cases are mostly linear. Means that we can just use the linear, we can find a linear relationship between 2 or 3 variables. But in most cases, that the data is oftentimes nonlinear. So, for example, here we cannot use a straight line to describe the relationship between the triangles and circles. We need to draw a curved line here to separate two groups. So that's why we need some methods other than linear regression to learn these patterns. Okay, so that is the whole point of the nonlinear supervised learning, which is the introduced today is the decision tree. Okay, so for this data, you probably will think that, okay, we can draw a vertical line here to divide the data into the left part and right part. So in this case, we will set the line here to separate anything below the 50 and anything above the 50 based on the x coordinate. Okay, so this is the first decision point we need to make. The decision here is that if the x value is larger than 50, then we will think they are green circles. If the values are below 50 or equal, maybe just below or equal, then we will determine that these are the red triangles. So you can see that if we just put a straight line here, it's just like a simple regression. And in this nonlinear case, it cannot work very well. So intuitively, we need to add the second line, which is we need to separate the two groups based on the y values. And in the tree model, means that we need to make the second decision here. So the second decision, we just plot the line in the level of the 30 here. So the second decision is that if the y value is below 30, then we will think these are the green circles. If the values are larger than 30, then we will think these are the red triangles. So the second decision helps us separate these two groups perfectly, because we can now make a decision model here. The first decision model is that first decision point is that if x is larger than 50, then we will continue to consider if y is also larger than 30. Then if the answer is yes, y is smaller than 30. If the answer is yes, then the result must be green circle. If the answer is no, then result should be the red triangle. And likewise, in the first decision point, if the answer is below the 50, then it is also in the category of the red triangle. So back to this graph, you probably will understand why we will make different decision point in different level of the tree. So using this simple example, then it should be very easy to understand the principle of the decision classification tree here. Okay, so this is a little bit more complex example. And in some cases that we don't just do classifications. In this case, we actually will classify different regions of the data into different outcomes. And these outcomes might be a continuous variable. For example, although we still have two features here, one x1 and x2, however, the blue dot and red dot here does not necessarily mean just two classes. They means that they have a different level of outcomes. For example, in this corner, they have outcomes of 0.4. And in this corner, they have outcome of the 1.0. And this one have the 0.123, etc. So now we can also use the decision model, tree model, to differentiate different level of outcomes, and that is the concept of the regression. So we can build a more complex tree models to divide these data into different outcomes or different corners. Then each outcome is corresponding to a certain outcome value that is continuous. So that is the simple regression tree. And so using these two examples, then you should be understanding what is the classification tree model and what is the regression tree model. So depending on the outcome, if the outcome is the nominal state, which means that they do not have they have category variables, then we are doing a classification tree. And if the outcome is a continuous variable, is ordinal variable, then we are doing a regression tree. Okay, so the general principle of the decision tree is that we always have a root node, and this root node contains all possible conditions, or you can say that it contains all data in the first level. Then we can make the first decision to divide the data into two groups. Then for each splitting, then we will divide the data into further the next level of the decision node. And for this decision node, we probably will result in a terminal node. For example, the yes, no, yes, no. In some cases, then we will reach a terminal node that means that there's no further decision can be made in these conditions. And in those cases that we can still differentiate different conditions, then we will draw another decision node to try to until no decision can be made. Okay, so in these tree models, then we will have several terminal nodes. And again, if these terminal nodes are categorical variables, then we are doing a classification trees. If these terminal nodes are continuous variables, then we are doing a regression trees. So that is the general representation of the decision tree. I hope you just use this figure and easily understand the general principle. Okay, so based on this simple example, you probably will figure out there could be some problems with this model. And let me just make a little adjustment to our data to show these problems. So in the previous examples, I show you that I can draw just two split. One is on the x-axis and the other is on the y-axis. Then we can divide the data into two groups. Now, I just change the example to just move this green circle a little bit above these right lower corners. So you probably say that, okay, I can still plot a curved line to differentiate these two groups. However, if you want to do the decision tree, then you will encounter a problem here. The problem is that if you just you cannot just use two split to divide the two groups, because the first split here you can divide data into two groups, that is fine. In the second split, then in the previous example, in the second split will result in the perfect classifications. But because of this data, then we will need a further two split to define the group into divide the data into two perfect categories. So that is the problem, is because this may be one way to do classification tree, because we can first do the x-axis, do a split on the x coordinate, and the second split on the y coordinate, and the third split on the x again, and the fourth split on the y again. However, we can always find another way to do the classification tree. For example, we can do the first split on the y coordinate and the second on the x. Then we can always find different ways to divide the data. So there is a problem with the decision tree, is that there seems to be a high variance of ways of classifications, and that is the problem. Another problem is that you probably can always find a way to perfectly differentiate two different categories or three categories, as long as you just draw many decision points. So that is a problem, because although we can find a perfect model to describe the data, but sometimes this model can be overfitting. Okay, that is problem. So what is overfitting? So let me use a simple example here. So here the blue dot are the real data, the ground truth, and the red line is the model we try to describe this data. So in the left case, we describe the model by the several connected red lines to describe this model. And you can see that this model has a high variance, because for each line it has different characteristics. So we use many features to describe this model, and it could be just overfitting, because in the other data you cannot just use these lines to describe the same phenomenon. Okay, so in the middle case, then we just use a horizontal line to describe the model, and of course you can visually see that this is not accurate. The model has the high bias compared to the left one. It has a small bias, but it has a high variance of the model. So ideally or optimally, then we should find a model that has the low bias and also the low variance. But the bias and the variance are sometimes a trade-off. If you have a high bias, then you have a low variance. Then if you have a low variance, then sometimes you have just high bias. So it's a trade-off between the bias and the variance. But let me explain what is the variance and the overfitting and the bias. Okay, so if we have a dot, and the central the circle here is a ground truth. And when we shoot the dart, then in this case we have the underfitting, because then the dart is the final result is away from the ground truth, so it has a high bias. But although in this case we have a low variance, so in other way, this one has a low accuracy but high precision, because we always shoot the dart in the same place, so it has a high precision but low accuracy. So in other words, it has a high bias but low variance. And the perfect condition is that we have a low bias and low variance, means that we not only we accurately shoot the dart into the right position, but also we have the high precision, which means a low variance, and each trial is consistent with each other. And in this case, we have not only the high variance but also high bias. So no one will want this model because this is totally failure. Okay, but sometimes we will have this kind of model because it has a certain degree of the accuracy if the bias is relatively low, but the variance is high. So in this case, we consider this overfitting because we just fit a model with the high variance conditions, although we contains all possible conditions, but it cannot describe in a precise way. So that is the concept of overfitting. And in the right figure, then you should be able to understand there is a trade-off between the bias and the variance, or accuracy and the precision. So we need to find the optimal the region that can have a balance between the accuracy and precision, or the bias and variance. So this is just a basic terminology of the machine learning. I hope you understand this one. Then we will continue to the solutions. Okay, so now we know that in the decision tree model, it can have a high variance because you can begin with a different decision nodes or decision informations. Then the results will be very different. The tree will be different from one to the other, just based on the different starting points or different decision nodes. So for the same data, you might derive the different predictions. And the solution to this is we just try to do many times of predictions. And we know that each predictions will have a different tree representations. So the first solution is that we probably just want to average all predictions to find out what is the mean representation, the average representation of this tree. The other technique is that you probably can use a democratic rules, for example, the majority wins rules. Then we will find what is the majority patterns of these trees, and that majority patterns will be our final results. So the decision tree, if we incorporate the random forest concept in the decision tree, then we will have the so-called random forest decision models. It means that we just try to look for a large ensemble of the different trees to find out optimal solutions. So that is the concept of the random forest prediction. So use this example then in these training sets, we can find many solutions to divide the data into the red and green dot. But uh, we can try to find out the majority representation of these different trees and to reach our final decision. So that is the concept of the random forest decision tree. It means that we need to uh, do many times of the tree classifications using different starting points, different decision flows. Then, but overall, we will still find out the majority representation or average representation of these trees. So that is the basic concept of the random forest machine learning models. And this is still another example. Just try to make you a very clear impression that how this works. So for each tree, we just follow a certain rules of the decision points. For example, here, then the first is the F1 is smaller than 0.56, and the second one is follow F2 smaller by 1.95, and so there's the third decision point that back to the F1. So by using this way, then we can divide the data into these representations. And but well, if the data has noise, then we can always find the different ways to classify this data. Then eventually, if we have a large collection of these trees, then we can find the consensus of the tree model to describe this phenomenon. So the random forest decision trees try to incorporate the noise. But eventually, if we average the tree, then this noise should be canceled and we can find the final solutions. So I just use a simple example here. So here we have a y equals to a combination of the x plus the sine x and also plus the noise. Here I didn't plot the noise here, but this is from the example from the internet. But just I think it's a very nice example. So you can look for the example on this website, and of course for this data we can plot a straight line, a linear regression, to describe this example. But also we know this is nonlinear, so we can also use the decision tree to describe this sine curve. So here is the result. So the gray line here describe the linear regression results. And the orange line here describe the decision tree models. You just try to use different cuts, different split, and to simulate the change in this sine wave. Okay, so of course you probably can understand now that for the decision tree we can always have different representations. So if we add up these different representations using the noise, then we can find out the variance of the decision tree is quite high. Comparing to the linear regression, it has a relatively low variance, but there's a high bias here because the line cannot always describe the difference between the peak and trough. Okay, but for the decision tree models, although it has a high variance, but it can always follow the line. So it has a low bias but high variance. So that's why if we incorporate the random forest, which is the ensemble of the many different trees, we find out the majority of these trees, and then we can narrow down the model and to be in a more reasonable way, and we can find out a reasonable model to describe this the sine curve. So that is the improvement of decision tree based on the random forest. It can reduce the variance of our model and also maintain a relatively high accuracy. So that is the beauty of the model. So decision tree is developed in the early time, developed over than 30 years ago, and it has been applied to the many areas of the data. It is very easy to use, but as I said, because it has a high variance, so later time has been replaced by the other techniques, other nonlinear methods. But because of the random forest development, so now we can still use the decision tree to reach a quite reasonable model. So for example, here in the medical area, if we have the genetic data, then we can use this decision tree to reduce dimensionality of our genetic data into a reasonable size and to do the genetic associations. Or then we can use this state decision tree model to classify the patient's phenotype into the healthy or disease phenotype. So that is the one common applications of the decision tree in the medical areas. Okay, so let me just try to do a simple comparisons but of different supervised learning techniques. I already showed you these slides in the introduction, but now you should have more insights into these figures. So for the regression, then we already know that it's a linear line and that can separate two groups, and it's not perfectly, it has a high bias but relatively low variance. And for the decision tree models, we can improve this by just using several decision nodes to describe the data. So it's a nonlinear method here. Then we can also have a support vector machine to fit a nonlinear model. And for the neural network, in most cases, it just resembles the linear regression. And for the random forest, we can find many different solutions. Then we find the consensus trees here. Then you can describe the model very well. And for the three categories data, then you can also find the two lines to separate the data, but also you can use the nonlinear methods to find a very complex separation of these data. So these are just give you a flavor that how different supervised learning techniques can do the work on the same data. Okay, so in the first part of the course, I just give you a very simple explanation of the decision tree models and also how do we overcome the limitation by the random forest. And to summarize these, the knowledge and the advantage of the decision tree is that it is very easy to explain. You can just follow the tree to do the classification or regression, and it can be displayed in a graphical way. And also, it can easily handle the qualitative predictors. So remember, in the regression model, I already showed you how to process the category variables using dummy variables. But in the decision tree, you don't have to do this. You just use the decision nodes to make a yes or no questions. So you can easily handle qualitative predictors. But there are limitations. One limitation is that it has a relatively low level of predictive accuracy. So it has a high, even it has in previous slide I showed you that it has a high variance and low bias. Means that it has a higher accuracy than the linear regression, but compared to the neural network and other advanced models, it still has a relatively low level of accuracy. And the most important limitation is that a small change in the data, just like I show you in the simple example, if you just change the data, then it can result in a large shift in the final estimated tree. So in the first example I show, you can use only 2 split to describe the data. But with a small change, you need to do the 4 split to describe the data. So that is a very serious limitations. So that is why if we incorporate the ensemble methods by aggregating many decision trees, then for example we can use the bagging, random forest, and boosting. And here I just show you the concept of the ensemble, which is random forest. Then we can find out a reasonable model that can have an optimal or balance between the bias and the variance. Okay, so that is the decision tree, and I hope you enjoy this lecture part, and then we can continue our journey to the workshop part, and then try to use the MATLAB to do the decision models.